I'm looking at where I've gotten to in the presentation, and I need to talk a lot faster, so I will start to do that. Here's roughly where we left off. So if you want to self-manage the information, you need these three things, and you don't need friction. So how do we deal with that? First, we jettison the host abstraction. It gets in our way, and it provides no value. The way that you usually get ontology is via hierarchy. You get meaning by organizing your knowledge in a structure, hierarchical structures typically. We do that, and they're represented as hierarchical names. The provenance we get via signing. It's the cryptographic primitive for giving provenance, for establishing identity or asserting identity. And a particular type of signing. What you want to sign is not the name, and it's not the data, it's the binding between them. That's what's important. And I need to give an example of this. So in the last 8 years in the US, we learned a lot about lying. And there are two styles. There's a Cheney-Bush lie where you just make something up and say it, right? Just corrupt data. If you sign the data, if you have self-certifying data, you can detect that kind of lie. But there's another style, there's a Rumsfeld-style lie, where you give a true answer to a question, but not to the question that was asked. So somebody says, are there really weapons of mass destruction? And you say, yes, I had oatmeal for breakfast. That's harder to detect. Right? If you just have self-certifying data, it certifies, but it's totally irrelevant. And the only way that you can establish relevance is by looking at meaning in context. And it's the ontology, it's the name that gives you the context. And so if you want to prevent that kind of attack, which is the very common kind of attack because it works so well, you need to certify bindings, not just the data, not just the names. So that's how we generate provenance, signing everything. And the way that you get locality is you make visible at the network layer the way that bits flow. Bits diffuse from a producer to a consumer. That's the way the network works. Right? We can't teleport them. They have to move. But since the early days of telephony, we try to pretend that's not happening. When you're talking to a telephone, you view yourself as talking to the person on the other end. You're not. You're talking to the phone. Right? And then there's some complicated electrical things that are happening, and your conversation is diffusing through a network and is being reproduced on the other end. But you're talking to something local. When you're communicating to something local. If you make that explicit, if you say, hey, that's the way it works and I'm not going to try to hide it from you, then you can use that locality as part of your engineering. You can make that awareness both part of your protocols, and you can expose it higher up in the stack. So we don't try to abstract that out. We use a diffusion model. And the way that you get rid of friction is you correct a mistake that John von Neumann made, which is thinking of information in terms of its containers. And I want to talk at some length about that. And it's on this theme. Security on the internet is really bad. It just totally sucks. And that's not because of sloppy programming, though there's a lot of sloppy programming. It's far more fundamental than that. It's because the way that we view information is not the information itself. Right? We can't name information. What we can name is where it lives. We can name its containers. So when you get a web page, you get it from a host, right? That's a container for a bunch of web pages, and you get it from a file on that host. In your mind, that's what you're referencing. You hope that the bits in that container are what they're supposed to be. When I reference a web page on my bank, I really hope that they put those bits there, and it's the bits that they intended to be there. But I have no assurance of that, and they have no assurance of that. Right? It's very hard to know what's in a container. But it's the basis of computing going back to the very early days, and that was the world that I showed you in the 60s and even earlier in the 50s, machines were very expensive, memories were tiny, so disks were kilobytes. My first computer had 4 kilobytes of serial delay line memory. It was a serial machine in the early 1960s. And that was a lot for the time. It actually had a Fortran compiler on it, in addition to the normal utilities. You could do that when you had whole 4 kilobytes of memory to deal with. And it didn't have a disk, it had a paper tape reader, which would accommodate, I think, 12 kilobytes on a spool of tape. These were the size of memories that we had. It's one reason why data didn't live on machines. And because of that, when you wrote programs, you viewed your data as coming from some external source, which you abstracted, the tape drive, or staging the data into a file on the disk, and so you would read from input, which is a container where you dumped your data, and you'd write to output, which was another container where you'd put your results. But you never dealt with the data directly. You never named it directly. You couldn't, because you had to keep replacing it because all the storage that you had available was tiny. Right down to the machine level, we didn't have a lot of high-speed memory. So machines had registers, 4 or 8 locations of high-speed storage, and you did computations in the registers, and then you had this much slower RAM, which was little ferrite cores, where you'd store the results and you pick up new computations. Right? So we got into this mindset of naming the containers to operate on their contents. But that's totally insecure. Right? You can't know what's in a container. And for many years, for decades, both John Bacchus of IBM and Tony Hoare, now of Microsoft Research, got the ACM Turing Awards for preaching against containers. They say it's the source of all bugs. You really don't know what's in that container. Even if you try and track its history, if you've got any sort of parallel processing going on, something can overwrite it. For security properties, even though you elaborately seal it, Ron Rivas gives a talk about the fallacy of the unpickable lock. He says, a lock by its nature has to be opened. If it can't be opened, it's useless. Right? You might as well weld whatever's locking shut. But if the lock can be opened, it can be opened by good guys and bad guys. Right? Lockpicks work just as well as keys. There's a whole class at MIT on lockpicking, because a container, by its nature, you need to be able to replace its contents. If you can't do that, it doesn't fulfill its mission. But if you can replace its contents, the bad guys can replace its contents. If you look at all of the attacks that are currently extant on the internet, they have to do with attacking containers. Most common ones being things like cross-site scripting, which is make a container, make a web page, point somewhere other than the user thinks it points. But you can attack many other kinds of containers. You attack the host container by attacking ARP so that you get the MAC layer to IP address binding, by attacking routing so that you get divert the path binding, you route your data through somewhere else, attack DNS by attacking the name to address bindings. All of these things are levels of indirections, ways of doing containers, moving you away from the data, that are easy for attackers to circumvent. If you want to really secure data, you secure the data, not the thing that holds it. And that's easy to do, right? The containers are another thing that was not God-given. If you develop any sort of code, you probably use some version control system, Subversion, CVS, Git. There, they say, I don't want a file container because I'm sitting there hacking on something, chugging along for an hour, and I go, oh, damn, that's never going to work. I want to back up and start over again. Well, if I had a container, where I was is gone. What I've got is the hour of mistakes that I've been making. If I've got a version control system, not a container, then it's keeping the whole temporal history. I see myself as working on files, that's what my editor sees, but in reality, I'm working on this tree-structured set of information which captures all of the versions, and I can go back in time, and I frequently need to do that. And it's a model that presents itself as a container, but it's a lot like if you're doing compiler work, you know, the first thing that you have to do to transform program into code or into some form that you can optimize it is go away from the assignment form, the A equals A plus 1 form, into an SSA form, a static single assignment, where you distinguish the two values of A, the one before the modification, the one after. You give them two different names. So that's adding some temporal annotation to the container to turn it into the name of data, not what it contains. So there's easy ways to go away from the container model while still preserving the illusion of containers, letting users deal with names like containers, and they can only dig into the details, see the temporal evolution if they need to, like they need to roll back in time. And if you do that, if you move away from a container model and start talking about the content itself, then you get something that's really easy to secure. You can secure the actual content by signing it. And we've known how to do that for 2 decades in ways that are absolutely unbreakable. Nobody can tamper with that content and not modify it, you know, not make the signature invalid. We do that, we make it immutable. So that is, we have a collection which are the versions of that content over time, and each one of those can be signed, and so the integrity of each one of those can be assessed. So that's what we do in CCN. You get rid of containers. What a CCN name names is a collection of data. This is our content model. So we're not ever naming a repository of data. We're naming a set of data. That set may have a single item in it, a single data value. It may have multiple items in it. Anybody can add to the collection. The set is defined by the naming structure. So the set of all items, the collection is a set of items with the same prefix. We have this hierarchical name structure. And there's no single system of meaning. You can't ever describe an ontology or a hierarchy that captures all meanings, captures every way that you want to represent your data. But the web gave us an easy way to deal with that. You put in links. And in general, you want to put in symlinks, right? So you have a name whose value is another name, and that connects one view of data, one way of naming with another view of data. It can connect anywhere in the tree, so that you can turn your ontology tree into an arbitrary graph. Okay. I want to make that more concrete. So here's an example of a name for that calendar application. So the prefix up there, park.com, van, cal, so that's the collection of all my calendar items. I'm at Park, so they gave me a prefix under their prefix, right? A place to make names. One of the things I want to name is calendar items. The particular one that I was dealing with, that pointless meeting, could be some vCard file for my card application. It's evolving over time because all those meetings seem to move around so that they can sort of do the maximum damage to your day. So this is version 3 of that meeting because it's been moving around a lot. So that part of the name captures the temporal evolution. You deal with things that are all different sizes in the world, but you don't want the network to deal with things that are all different sizes. Right? The smaller the unit you can put on the network, whatever the maximum size unit, that's the granularity of sharing. And if you put really big units on there, you're not going to share very efficiently. And you can either, between the objects in the network, you can put some fragmentation protocol, that's the model of TCP, or you can say, if I can name collections, which I need to do, then a collection of fragments is a collection. And I don't need another namespace in order to bust things up into pieces. I just name the pieces. And so you get some parsimony and you get some very nice things happening at the protocol level that I'm going to talk about later. So that S0 says this is segment 0. It's the first piece of whatever this item is. This item only has one piece. And then the last is either the content or a proxy for the content. It's currently using SHA-256 checksums. So if you want to name right down to the content level, these bits and no other bits. Right? So this calendar item, as it was on today, July 22nd, I can name those bits. I can make a link that points to those bits. Can't be forged. It's always going to resolve to them, no matter how this entry is changed, right? Because I put the bits in the name. It's a proxy for the bits, right? It's a finite length proxy, but it's unforgeable because it's a one-way checksum. If I'm replying with the data, I can compute that proxy from the actual data, so I don't have to put it in the name when I'm returning the data, and it can still be validated. But this is, names of this form is how you validate the binding between the name and the data. You essentially put the data in the name. And this is another idea of Ron Rivas. It came from a system that he did called SUDSI that I'm going to talk about in a little bit. Thing to say about this is the binding that we're doing here is immutable. Right? So I can make other objects like this, but they're new objects. If I change the calendar entry, I've changed its name, because if nothing else, I've changed the bits on the end. And I may remember to change the version number, I may not, but I've made a new item if I change any part of this. Right? So because of that, I don't have the coherency problem that I do if I'm talking about containers. Right? Whenever you try to replicate content, when you have a container model of the world, you have to make your replicas consistent with the master copy that lives in a container somewhere, that lives on some machine that defines the content. We don't have locations for content. The content itself authenticates itself and identifies itself, no matter where it is. And you don't have to be consistent with any other copy. You have to be able to validate this copy. This is a legitimate copy of version 3. You can check the signature and make sure that's true. What that means is when you're doing coherence protocols, there's nothing that can happen that can make what you know wrong. Right? Nobody can change this version underneath me. They can create a new one, so they can make my knowledge incomplete, but they can't make what I know wrong. And that completely changes the operation of the replication, the consistency, and the coherence protocols. And there's some great work, system called Practi that's been done at UT Austin, where they teased apart the replication of data from the storage of data, from the containers of data, and said, if you could name the data, then you could give independent control of the replication and the coherence semantics. And you can do more than give independent control. Each receiver can choose the coherence model that's appropriate for that receiver, which means that a lot of the consequences of coherence, which are serial consistency, which forces you to do things really, really slow in a distributed system, you can make that go away. Because your backup program doesn't need to be serially consistent, it just needs all the data. Right? And because you've decoupled the semantics of consistency, you're not dependent on a container, you're just dependent on getting all the data, you can use a system like Practi to make the consistency and coherence be receiver specific. Means that you can choose to operate in a lot of different performance regimes, and by default, you work in a very parallel, very high performance regime. Provenance, I've waved my hands about signing. Here's some more details on signing. So you take that whole name, which includes the content on it, and the thing that created that data, the last thing it does, my calendar program, the very last thing it does is it signs the whole thing, and then it injects it into the network. That's done at the bottom of the app, right? The app's interface to the network stack. It's not done at the kernel, and the reason for that is to make the attack surface as small as possible. The creator of the data, as close to the creator as you can possibly get, that entity signs the data. It seals it, attests to its integrity, and nothing after that point modifies it. Within CCN, IP packets get rewritten at every hop. They have to be so that you can update the TTL. In CCN, packets are never modified. And if they are modified, you can tell. So the program that created that signed the data. It had a signing key. That was its key. And in the packet, there's a key locator, something that points off to the key. The key can live in the packet. It can be a pointer to the key somewhere else. Generally, it's the name of the key. And in general, it's a rule that tells you how to go from the name of the data to the name of the key. A very nice thing about going to a content-oriented model where you actually name the data is you don't have a key distribution problem, which is the Achilles heel of all security systems. If you've got a container view of information and an armored pipe view of the way that information flows around, there's no way to associate the key for a set of data with the data itself because you don't have a name for the data itself. Right? You're not dealing with the data, you're dealing with an SSL connection that gets you the data. How do I get the key associated with that data? Well, I can't because I don't have a name. In CCN, you've got to have a name to get anything. The name is the fundamental to the communication. And you can always algorithmically go from a name to the key for the name. Right? You can just say, the key associated with this name is the name/key. Right? And if you want to go get the key, you present that name. And then you use the CCN mechanisms to retrieve it, because that's just another named data item. So you get absolutely trivial key distribution at an arbitrary granularity. It could be at the data item level, the single kilobyte level. It could be at the whole collection level. It can be at all your data level. You get to choose. But there's no technical barrier to making it as fine as you want it to be. So my program signed it with a signing key that I gave it. The way I gave it a key was I had a signing key that Park gave me when I was employed by them. So they gave it to me when I delegated. They delegated that part of the namespace. In fact, the delegation is giving me that key. So I use my key to sign the calendar program's key. And the calendar program uses its key to sign the data items. I'm not giving the calendar program my signing key, right? I'm delegating it the ability, I'm giving it a delegated key, a longer key. And the reason for that is you notice that the name of that key matches the leading name of the data item. And in our library dealing with collections, at the application level, we use that convention explicitly. We say, that's the realm in which this key is valid. So this key can be used to sign a calendar entry. It can't be used to sign a check. Right? It's a key, meaning is a very limited domain. If it's compromised, well, I'm sad, but the damage is limited. And that's coming for free. That's coming, again, because we've got these structured names. There are other things that can be checked from the same name. This goes across Park's network, doesn't have to, it could go across Bluetooth or other things. But if it goes across Park's network can check and say, if there's a data item that claims to be in the park.com namespace, it better be signed by a key that was authorized for the park.com namespace. So the network infrastructure is going to check that part of the signature and say, is the user of this namespace somebody that I want using this namespace, or is it somebody who wandered in off the street and is trying to inject data into us? And if the Park part of the key doesn't validate, the infrastructure says, nope, that's my namespace, you're not authorized to use it, I'm throwing this away. So that's the flip side of attack amplification. Right? Now, the attacker has to work against the entire network infrastructure. Right? You want to inject bogus stuff into Park, the first Park box that it hits says, you want to, my guys? No, sorry, your data's gone. Right? So rather than having a lens, we've turned it around and we can make all of the infrastructure defend us because the content's visible. What we're trying to accomplish is visible. And it's visible both at the data item level and at the certification level. The infrastructure can make the connections and use that to protect. So I'm going to use that as a segue to the security model. So I think I've said pretty much all of this. For TCP, because by design the content's opaque, it can't help you in protecting it. All it can do is put an armor shell around it, but that can hurt you more than help you. We have this totally horrible trust model, again, because of our communication, armored pipe containers talking to hosts. We try to do this root certified trust. That means you're outsourcing trust, and in my mind, that's the same as outsourcing breathing. It's a really bad idea, because trust is how we live. It's what makes our communities. But you don't get to do that at the network level. You have to trust who Microsoft trusts, or you trust who VeriSign trusts, whoever the root authorities are that can sign certificates. The intent was there would only be a few of those. They would be quasi-governmental agencies. They'd work with very high level of ethics, very high level of checking. Well, you look in the current Microsoft Internet Explorer, it lists 263 root authorities. They're from all over the world. Most of them I don't recognize. Most of them I wouldn't trust for a second, including up to particularly Microsoft. But my browser trusts them implicitly. Anything they certify, any of those authorities can certify the certificate that claims to be my bank, and my browser will believe it because a root authority asserted it was true. They didn't actually have to be the root authority who gave the certificate to my bank. Any of the root authorities are equivalent. So any of those 230 guys that gave a nickel to Microsoft, right, they're an absolute sort of source of trust. And all your devices absolutely trust them. Anything they say, it believes. This is not a good world. It's just way too much attack surface, way too many high-value targets. If I want to protect my data at a fine granularity, so if something's compromised, I don't lose much, because I can't name content, I can't name keys. So I get this completely unsolvable key distribution problem. When I try to set up security policies, like inside an organization, the way that people think about information security is in terms of what can be shared. Right? I have this set of information, I'm collaborating with you, I will share that set of information, but no other set. Right? That we work on the information, it embodies our interaction. But you can't express that kind of policy at the network level because the network doesn't know about what, it knows about who. So what you have to express at the network level is who can talk to who. Your machine can talk to this machine via the firewall, and I'm careful to put on that machine the stuff that we can share. Right? So I try to manually make the what congruent with the who, and that doesn't work very well. Right? I can't put a separate machine for every project on the firewall, and if I mix a lot of it together, well, the sharing might not be what I think it is. The information can diffuse because there's not a hard boundary, and I can't check it because it's not visible to the network. The network just knows about things at the machine level. Okay, so the next few slides were largely dictated by Diana Smithers, our security guru, because she claims I'm totally incompetent to talk about security, which is completely true. So I'm going to be giving you her words with a little bit of annotation. So in CCN, we changed that. In CCN, every packet's authenticated, and it's not only authenticated, but it's publicly verifiable. Anything can verify any packet. Now, that's very different than current practice. The best current practice, it's fairly rare, but the best that you ever do in a TCP IP network is what's called HMAC, a hashed message authenticity checker. And what that is you take a secret, like a shared random number that some set of participants know, you concatenate it with your data, then you can compute a one-way checksum of all your data plus the secret. Right? Since it's a one-way checksum, you can't go from the checksum back to the data. So only the people that know the secret can authenticate the data. But anybody who knows the secret can authenticate the data. The problem is it's completely symmetric. Anybody who can verify can also forge. There's only one secret. And only the people that can verify can attest to whether or not there's any data integrity. No other party can, in particular the network can't. We do something different. We actually sign the packets. Signing, you do the original view, is you compute a one-way checksum of the packet plus its name. And then you encrypt that with your private key. And in the packet, you put a locator for your public key. So now anybody who gets that packet can take your public key, decrypt the checksum, and then separately compute the checksum from the data. If those match, they know that the data hasn't been modified, and the fact that your key, your public key decrypted the checksum proves that you were the one that signed it. Right? So you're getting not only message integrity, but you're getting the authenticity. Who signed this message? You're getting it from the public key crypto. Now, that computing a signature is expensive, for some measure of expensive, right? Somewhere between 100 microseconds and 3 milliseconds, depending on the algorithm that you're using on a current generation Pentium, 2 gigahertz Pentium. You don't have to compute a signature for every packet. There's lots of ways. Thing that was invented by Ralph Merkel called a Merkel tree, where you can use one signature for a whole collection of data, but you can put the incremental computations that go into that signature physically in the packet. Packet has to contain the log number of those. So if you've got 1,000 items, you need 10 partial computations in every packet. But you only do one signature computation. It's very cheap, so you can get very high level of amortization. There are similar things you can do with what are called ticket signing mechanisms. So you can make the signing operation be arbitrarily cheap. You can make the verification operation be relatively cheap. You can also make it probabilistic. It's the receiver that can choose what they choose to verify and when. They can choose to verify the first packet and trust the following ones. They can choose to verify every nth or some random number. They get to choose their amortization schedule. The big thing that you get from public verifiability is if you're allowing content to be replicated, if it can live at multiple places, you have what's called the Chinese telephone problem, that each of those copies can pick up errors, and the errors are persistent, because they live in the replicas, and then you make another replica and it has more errors. It has all the original errors plus new ones that came from the transcription. You need to be able to get rid of the replicas that contain errors. You don't want them to live in the network because they can impede your communication, they waste space. And attackers can inject data where they pretend it's signed, but it's not. Right? They don't know the keys that were necessary to sign it, but they can put all the metadata that looks like it's got a correct signature. And unless you actually do the check, you can't tell that the data is a forgery. You don't want to do that at every node in the network. You would like to do a system where the end nodes, the consumers of the data, check the data. And if they find that it doesn't check, they can go back to the infrastructure and say, that piece of data that you gave me was bogus. Now, the infrastructure, they don't know if you're telling the truth or lying. But if it's publicly verifiable, they can check and say, oh, you're right, it's bogus, and it looks like you're a trustworthy guy. If you tell me in the future, I won't bother to check. You can build up reputation systems and gossip systems that let you distribute the work of verification in the presence of replication so that you get valid replicas everywhere, doing the work at the edge, so you get scalability. As the edge grows, you get more places to do the checking, and you don't tend to concentrate the work in the center. Okay. Trust model, so you have to do security validation in some sort of trust model. And as I say, the one that we've got now, the God's anointed by the root authorities, they determine all trust. Right? That's a really bad one. Ron Rivest, who is one of the true gods of security, is the R in RSA and has invented just an incredible amount of fundamental security infrastructure. He got very frustrated by the state of certification in the 1990s. And he invented a very nice certification system called SUDSI, Simple Distributed Security Architecture. He published it in '96. He took it into the IETF, tried to get it standardized. It turns out that was a very frustrating experience. Some RFCs got written, but it didn't have the impact that it should have, in large part because it's a model that's really focused towards content, and IETF networking isn't content. But it's simple, it's extremely robust, it's completely distributed, the choices are completely local, you don't have to coordinate with anybody or anything. But it's been fully axiomatized. You can express it in formal logic, and you can validate that formal logic against standard security models, standard threat models. It means it's verified. That, I mean, you really can depend on it at a first principles level. And so in the slides, these are links. That's to Ron's SUDSI page. The axiomatization was done by Joe Halpern, and that's a link to his paper. It was done in '99. That's the trust model we use. I mean, it is very good, and nobody can match Revist for designing these kinds of things. You use a lot of keys, signing keys for authenticity, and encryption keys for privacy. And you can make the keys be largely automatic, and that's a benefit of the names, because it's really easy to tie keys to data. It means that I make some new set of data, the policy says it wants to be private. Part of making the new set of data, I generate a random number, that's the key. Right? Then I encrypt that key under my public key or under group keys, spread it throughout the world so they're replicas and it can't get lost. Now that data is private. And it's made private, right? It never lives in the clear. In normal networking, that would give you an unsolvable key distribution problem, but CCN is perfect for key distribution because you can name keys, and anything you name you can distribute. And they're replicated so that you get very high reliability. The way the SUDSI trust model works is when you have these keys, particularly signing keys, the reasons that I use for trusting a key don't have to be the reasons that you use for trusting a key. So I get a key from my bank, and I decide that I'm going to trust that because when I set up the business relationship, we exchanged keys. And the key and the message from them, I can prove to myself it was derived from the key that was established when we did our business relationship. And that's the way I want to do business with my bank, right? I want to have a very high level of trust in the communication, and if I get a key that I can't trace back to the business relationship, then I don't believe it's my bank. That's my choice. You get a credit card offer from my bank. You look at it and say, well, did this really come from this bank, or is it from some scammer? You can check the key in a registry of keys. You can check with your friends to find out if they've seen that key before. The way that you establish trust in that key has to do with your context for the information, how you value the information. As opposed to today, where there's a one-size-fits-all. We check with VeriSign and see if they sign the key. There's a fundamental change that happens at the network management and the network configuration level when you put in security at the bottom. And now these are my words, not Diana. So John Maynard Smith, the evolutionary biologist who gave us evolutionary game theory and a lot of mathematical insight on how ecosystems and organisms create themselves, how they self-organize and structure. In one of his books, he said that identity creates organism, that the thing that's fundamental to making an organic unit, a cooperative unit, is a shared notion of identity. And you get it in things like bodies because our identity comes from our DNA. But we get it in other things like communities and families because of shared context and shared experience. You can't make networks today that behave organically that have levels of cooperation in the network because there's no notion of identity that you could use to bootstrap that organism, that cooperation. If you move to a content view, several things get easier. One is your configuration is dead simple. The only thing that you ever need to configure is the signing key. It includes the identity, and it's a structured key, so it includes your identity at many levels. Right? Your individual identity, but your role, I do calendars, your organization, I do calendars for Van in Park. Right? There's many pieces of information that are embedded in that identity that you can use to say who you should trust and at what level. But another interesting thing is in host-to-host communication, point-to-point communication, there's always two ends. And so you have to configure the two ends to agree. You have to configure the same information in 2 points. If you have to configure the same thing 2 places for stuff to work, there's a much better even chance that it's not going to work, right? Because there's lots of ways to misconfigure. If you don't have point-to-point communication, if you're talking about stuff, not to stuff, all configuration is single point. You never have to get agreement. You're saying what you want. You know what you want. Nobody has to agree on that for you to say it. They have to have it in order to respond, but they don't have to agree. Right? So you get this really robust configuration, single point configuration that you can't misconfigure because it doesn't have any agreement involved in it. And the configuration includes some notion of community and identity. And you can use that as a sense of self. So as you're learning about the world, you're learning about the things around you and what you should do in that world. When the outside world tells you things, gives you information, tells you about its context, you know what you can believe and what you can't believe. You know what's relevant to you because you can filter it through your identity. And they have to put their identity in everything that they're telling you. So you can say, I'm a router and you're giving me adjacencies and we're the same organization, we're the same network, I guess I'll believe your adjacencies. If you're not the same organization, you're not the same network, you've got a different signing key, well, I'm glad to know about your adjacencies, but they have nothing to do with me. So you get an easy way of getting trust without additional configuration. And the example that I gave about defending a namespace, all of the infrastructure can recognize not self in addition to recognizing self. Right? The two concepts are complementary. So you know what's not you. You know what you should defend against. And you can muster all of the infrastructure to protect things that need protecting rather than having to localize those. And we can't do that with current networks. And we can't do it because our security is an afterthought. And this is a deep annoyance of mine that we've always made security an afterthought, but it's not. It's fundamental. And it's fundamental to organisms, right? Security is what gives us identity. We tend to think of security in terms of privacy, in terms of encryption. But if you look at Riva's webpage, a lot of their work has been on signing, it's been on identity, because identity is a much more fundamental operation and a much more important operation. It's really a Swiss Army knife of security. And the privacy, I mean, that's interesting, being able to encrypt stuff and keep it private. That's good, but it's not nearly as fundamental. What's really fundamental is identity. And identity doesn't have to disturb privacy. In fact, it's the other way around. When most of Ron's recent research has been on micropayment systems and small transaction systems where the users want anonymity. And you use signing to create the anonymity. What you do is you sign the money so that you don't have to identify the principals. Right? And you can sign the money in a way that is not traceable. It's identified as money. It can only be used once. But you can't tell who used it. You can't tell what it was used for. And that's, again, it's a first principles assertion. It's a very hard guarantee of privacy. It's a mathematical guarantee that nobody no matter what information they have available to them. I mean, it doesn't matter if you're Dick Cheney, you can't tell who used this money to buy what. Right? There is no information that would let you reverse the spending operations and track it back. And that's from a signing operation. Right? It really is a Swiss Army knife, and it's something that we should be integrating into our thoughts very early, and we don't. At least the tendency in the US is, I don't do security, I don't know security, all that security stuff is magic, right? And that's a poor point of view that really impoverishes our world.